All right, so for question 1, part A, we're looking for the heterozygous parent genotype. And so we know that it's going to be crossed with a homozygous recessive parent over here. And so in order to find this, this genotype, we're going to look at the parent samples, the offspring, there we go. And one of them shows this phenotype, and one of them shows this other phenotype. And those are the offspring that have the largest number of that phenotype. And so we have these pluses to designate the wild type alleles, and then the letters without the pluses are to show the recessive alleles. And so we put those together, and that gives us the heterozygous genotype for the parent. And then moving on to part B, in order to figure out the order in which these alleles need to be, we take a look at what's the double crossovers. And those are the least amount of offspring. So for this problem, we see that these would be their genotypes. And we look at these double crossovers in relation to what we figured our heterozygous parent would be. And we wanted to see where the two genes had crossed over. And so in this one, if you take a look over here, it shows that compared to this, we have a wild type RG on the bottom and a wild type MG phenotype on the top. And so if we figure that these two have switched over, we know that those are going to be on opposite sides. So this must be in the middle. The A is going to be in the middle with the RG on the side. So we rewrote that over here, showing the order that the alleles are going to be in. And then for part C, in order to figure out the distance between the different alleles, we came over here and we wrote out all the different genotypes, and we wrote their frequency next to them. And then in order to find the difference or the distance between two of these, we figured out which one of these had crossed. And so for the first one, we're trying to figure out the distance between A and MG. So we come up here and we find that this offspring right here and this offspring right here, they've crossed A and MG. So we're going to use these in our formula over here. We're going to add up the double crossovers as well as this 13 and this 12. We're going to put it all over the total number of offspring that we have, which is 206, and that gives us 0.13. If we take that number, multiply it by 100, it gives us 13.1 mu, which is our units here, and that's the distance between those genes. We do the exact same thing for A and RG over here using these two bottom ones and these two on the top. Plug that back into our formula, divide by 206, gives us 17.5, multiplied by 100, and our total is 17.5 mu, so that gives us our answer right here. And then to find the amount of interference, we're going to take a look at these ratios that we came out with right up here. And so this is going to show the crossing over, the amount of times they're crossing over, and then that's going to give us a value. We're going to multiply this value by our total value to give us what we would think the expected outcome would be of crossing over, and that gives us 4.7. So we put that down here. And then 2 is the amount, the addition of these two double crossovers, and that's the actual outcome that we see versus the expected. So we put the actual over expected, it's 1 minus that value, and that gives us 0.57 or 57%. Okay.
So, for number 2, we have these 3 different genes. So we're looking for the arrangement for the heterozygous female. And so this is the graph that they gave us. And so these are the 2 parental types because they're the most abundant. And so what I did was I looked for the ones that didn't match the parental type. So these ones didn't match either of those. These SC and S didn't match, and these 2 as well didn't match. So you know that those ones had crossed over. And so I counted those up and divided it by the number that we had total, which is 1,000, and I got 33 mu. I did the same for the SV and the SC and V as well. So I added them all up. The ones that didn't match and divided by 1,000. And so you know that this one has the greatest distance, so the S and the V are going to be on the ends, which we see here, and then the SC is in the middle. And so for the female, we know that this is the parental type, so that's what hers is going to look like. And then for the map, we have the distances here, the 33 MU and the 10 MU between each of these. And then for the expected, I took the 33 MU and the 10 and divided them by 100 because I multiplied them by 100 over there. And I multiplied them by 1,000 to find how many expected we have, which is 33. So we did that, and then the observed is the two smallest ones, so it's the 14 and the 10. And so we get 1 minus 24 over 33, which ends up being 27%.
Go.
Okay, so the genes that we're looking for in problem number 3, we have glassy, coal, striped, and then these other ones are going to represent the wild type. And we have 1,000 total progeny. So for A, we take the largest amount of progeny, and I figured out their genotypes, and so we know it to be the wild type, and then the coal, and then the wild type S, and then we have glassy, wild type C, and then striped. So for B, I just rewrote it 3 times to figure out the different orders because we're trying to figure out the gene order. And so then you take the least amount of the progeny, which was 8 and 11, and I wrote out their genotypes here, and so then I just matched it up to see which one it matched with, and it matched with this one. So I put that right here. So then I wrote it out twice to figure out the double crossovers, first with crossing the S alleles and then with the C alleles. So with these ones, we don't have any progeny with just being, just with glassy eyes or with striped and coal bodies. And so I put 0 there. And then for these ones, we have 27 progeny and then 29 progeny. So then I added these ones up, divided by 1,000, and we got 1.9 map units between the S and G allele, and then added these ones up with 8 and 11, so that's coming from these two, like the least amount of progeny, divided by 1,000, which is the total number of progeny, and then multiply it by 100, and I got 7.5 map units between the G and C allele, and so I wrote out the map right here for you to see that. So then, to figure out the interference value, you take those map units divided by 100 and multiply them together, and we got 0.001425. And then you multiply it by 1,000. This is what you're figuring out to see like the expected progeny. And so we got 1.425. But the only issue is, so normally it would be the least 2 of the progeny, like so the 2 with the least amount. But the ones that were expected in the double crossover never even happened. And so it would just technically be 0 plus 0. And so you end up, when you put it into this equation for the interference value, you can expect, or we got 100% resistance because you never do see those phenotypes for the double crossovers.
Okay.
All right, so in problem number 4, we're talking about corn. And these are the different phenotypes, and I've just written them. Here are the recessive ones, and then these are the wild type for the genotypes. So for part A, it says determine the gene arrangement for these 3 linked genes. So we want to be able to figure out like what the parent genotypes are, and so we do that by looking at the information given with the phenotypes and the number of offspring. The ones that are the highest which is 385 and 379. Those are going to be our parents. And so those show the anther and then the brachydic and fine. And so then I just wrote the genotypes next to them. So you write them over each other, and that helps you determine the gene arrangement for those linked genes. So then for part B, it says determine the gene order for these 3 linked genes. So what I did is I just wrote them out and I just changed the order that they were in. And then you can like determine it going this way. I just circled them to show the different orders that you could have. So then you take the ones that are the least amount or the least number of offspring, which was the anther, fine, and the brachydic, which had 2, anther, fine had 3. And so then I just looked to see which of my options I drew out matched up with the genotypes of these. So I looked and I just like went through each one of these. So this one had the wild type of anther, wild type of fine, and then the recessive for the brachydic. And so that one matched, and so I just double checked with the other one, which was the recessive. Okay, so then this one is the recessive for anther, and then the wild type for brachydic, and then the recessive again for fine. So that helps you, so we know that it's going to be this one for the gene order for the linked genes. So then for part C, you're going to create a linkage map. So you need to figure out the distances between these ones. So I wrote this one, but I wrote it twice so I could figure out the different possibilities. So it could cross over and these 2 could switch, and then these ones could also switch on the end, since the fine genotype is in the middle. And so then I just circled those ones, and then you look at the information given and you're able to see that this genotype gives you 20 offspring. This one we observed 26, and then 87 for this one and 98 for this one. So then you add those ones up along with the ones that were the least over here, which were the brachydic and then the anther fine. You divide it by the total number, which was 1,000, and then multiply it by 100, and you get 5.1 map units or MU. And then do the same one for this one, and you get 19 MU. And so I just wrote it out for the mapping. So the distance between the genotype of brachydic, between that and fine is going to be 5.1, and then between fine and anther is going to be 19. So then for part D, you're going to figure out the interference value. And so you take those map units, divide it by 100, multiply those together, and you end up getting 0.00969. And so then you take that number, multiply it by 1,000, you get 9.69. And so that's what you would expect to get for the offspring. But what was actually observed was 5, which was the 3 plus 2 for the brachydic and anther fine. And so you divide those, and then you subtract it from 1, and you end up getting 0.484 or 48.4%.
Okay, so for question number 5, for part A, we broke it down, and this went back to the first week of class. So we drew out the cell breaking into individual gametes, and this one follows independent assortment, so they're not linked, and so they'll be able to split apart. And so the gamete genotypes that we ended up with was big A, big B, little a, little b, big A, little b, and little a, big B. And so each one of those, the frequency came out to the same, so the chance of those would be 1/4 for 5 part A. And then for 5 part B, this is where they are linked, but crossing over doesn't take place. And so the genotypes that we ended up with were big A, big B, big A, big B, little a, little b, and little a, little b. So obviously these 2 are the same and these 2 are the same, and so that shows that there's a 50% chance of receiving either big A, big B, or little a, little b. And then in part C, we have they're linked and crossing over takes place. So we showed the crossing over right here between this little a and this big A, and then that carries down and it produces the gametes, all 4 different type of gametes, which were what we saw in 5 part A. And so the frequency is 1/4 of each of these gametes. And then going to 5 part D, this one we had the map distance, so the distance between these 2 alleles was 7.8. So we worked backwards to figure out that 0.078, we put 100 as our sample size just to make the numbers easy, and that gave us 7.8. So that's showing us how many or how frequently this crossing over is taking place. And then we showed crossing over in our diagram here, and these middle 2 alleles are the gametes that are crossing over. So that represents the 7.8 that are taking place right here. The rest of these are following the parent population, the parent gametes, and so those are going to be what's left over, so 92.2%. So we broke those apart. So you have 46% frequency of big A, little b, big A, big B. You have a 3.9% frequency of big B, little a, 3.9% frequency of little b, big A, and a 46.1% frequency of little b, big A.